Hello everyone, and today we're going to be talking about stoichiometry. More specifically, we're going to be working through some problems involving stoichiometry, and we're going to be going through some simple problems and working our way up to some more complex problems. So join me if you want to learn a little bit more about chemistry. So stoichiometry problems are really just unit conversion problems. And to kind of start things off, I want us to start off with a unit conversion problem. So when we're doing unit conversions, we're just starting off with some amount of something, some variable that we're given, and we go through a series of equalities to convert it from that beginning unit to a different unit that we're looking for. So looking at this question, we have, using an authentic German recipe, you need to use 750.0 grams of sugar, or sucrose. You do not have a scale, only a regular measuring cup. How many cups of sugar are needed for the recipe? And then we're given some conversions, where we have sucrose density, cubic centimeters to milliliters, and liters to cups. So the first thing we want to do is figure out what we are given. What is the variable that we're starting out with? And in this case, it is going to be the 750 grams of sugar, or grams of sucrose. And then you may want to go ahead and figure out what is your final destination. Where are we trying to get to? And when you're reading the question, we say, how many cups of sugar are needed for the recipe? So we're looking for cups of sugar. All right. So normally when starting out these types of problems, I recommend starting off with the variable. And we can go ahead and write down the 750 grams. So we'll say 750.0 grams of sucrose. And then I like to use the row across method because that helps us keep track of our units. So whenever we're using this, we want to have whatever units here, and we want to have them diagonal across from it, so those will cancel out. So in this case, we need to try to find something with grams of sucrose to convert this from grams to something else. So looking at our problem here, we can see that we have the density here, where we have 1.587 grams per cubic centimeter for sucrose. Now what this number really means is that we have 1.587 grams of sucrose for every 1 cubic centimeter of sucrose. All right, and since this is an equality, we can flip those around, but the units of grams needs to be staying associated with this number. So if we go ahead and plug that in, we want grams of sucrose, so we want to put 1.587 grams of sucrose on the bottom, and then on the top, we're going to put 1 cubic centimeter of sucrose. All right, now that we're in cubic centimeters of sucrose, we can look at our units. We'll see that grams cancel out with grams of sucrose. And now we're converted it to cubic centimeters of sucrose. But we need to keep on going. We're not quite to cups of sucrose yet. So again, looking at our given information, we see that we have cubic centimeters right here. So that's what we're going to be using. So we're going to say for every 1 cubic centimeter of sucrose, we have 1 milliliter of sucrose. All right, so that's how equalities work. If we just want to go from one to the other, we can say that we have 1 cubic centimeter over 1 milliliter, or we can write it the other way as saying 1 milliliter over 1 cubic centimeter, just like we did. All right, so now we need to look for something that has milliliters of sucrose in it. All right, so we need milliliters of sucrose. Now looking at a problem, we don't see anything that directly has milliliters of sucrose. besides the conversion we just used. But what we do have is we have this liters to cups. So a very common conversion is to go from milliliters to liters. And you can use a useful equations packet for that, or you can just know that it's a very common conversion and say that we have 1,000 milliliters for every 1 liter of sucrose. All right, so now that we have liters of sucrose, we'll look for another equality, and the question gives us one where we have liters to cups. And so we'll say for every 1 liter of sucrose, we have 4.2268 cups of sucrose. All right, so now we want to go back and double check to make sure all of our units have canceled. So we have grams of sucrose canceling out with grams of sucrose, cubic centimeters of sucrose canceling out with cubic centimeters of sucrose, milliliters of sucrose canceling out with milliliters of sucrose, liters of sucrose canceling out with liters of sucrose, and that leaves us with our desired unit of cups of sucrose. So you can only cancel out units if you have one on top and the other one on bottom. So now we can go through and multiply everything on top. So I have the 750 multiplied by 4.2268, and then we'll divide by everything on the bottom. So we'll divide it by 1.587 and divide by 1,000. And so if we do all that math, what we should get is we should get 1.99754 cups of sucrose. We can go back and take a look at our significant figures. We can see that we have 4 sig figs on that first number. We have 4 sig figs on that lower number. Then we have some exact equalities, and then we have looks like 5 sig figs on that final conversion. So since we're multiplying and dividing, we have 4 sig figs, 4 sig figs, and 5 sig figs. We choose the lower of all of them, and our final answer is going to be limited to 4 significant figures to match that. So when we rewrite this, we have to say that we have 1.998 cups of sucrose or sugar. And so this would be the answer for, significant figures. But since this is like a real world problem, we'd have what would be the practical answer, because we're actually trying to make this recipe out, and we'd say is 2 cups of sugar, because we'll only be able to measure out 1 cup at a time. All right. So that's one way we can do unit conversions, and like I said, stoichiometry is very, very similar to unit conversions. So let's go ahead and we'll move on to doing a stoichiometry problem. Now for stoichiometry, it's just unit conversions, but you follow kind of a certain path as you're doing your unit conversions. It's a fairly regular process. And this is where we go from, we always want to convert to moles. And once we convert it into moles, that allows us to use our chemical equation. And we can say we can go from moles of one substance to moles of another substance. And that's why we're using that chemical equation. Once we have achieved that and got to our desired compound, now we can convert to our desired units of interest. So we're going to start off with a fairly general stoichiometry problem. So let's take a look at this. We have a highly reactive metal of sodium metal can be reacted with toxic chlorine gas to produce common table salt, NaCl. And we're given a formula of sodium plus chlorine gas yielding sodium chloride. So we have an unbalanced chemical equation here. Let's go ahead and balance it. So let's go ahead and take a look at this. We can divide it up into products and reactants. And if we look at each element one by one, we make sure it's the same on both sides. So if we're looking at sodium, on the reactant side, we only have that one right there. And if we look at the product side, we only have one right there. So we'll put one for each of those. It's balanced still. So let's go ahead and go to the next element. So now we'll look at chlorine. When we look at chlorine, we have this little subscript 2 here. That means we have 2 chlorines. And if we look at the product side, we see that we only have 1 chlorine. So that's not going to work because they're not the same. So in order to change that, what we're going to have to do is we're going to put in a coefficient. Coefficient is just a number that goes out in the front and says how many of those molecules we actually have. So we'll change this to 2 sodium chlorides. Now that we've done that, that 1 now becomes a 2 for our chlorines, but we also had sodium in there, so now the sodium has changed. So now, instead of 1 sodium in our products, we have 2 sodiums in our product. So now we need to go back and look at sodium once more. So we need 2 sodiums over on the reactant side, so we'll put a 2 coefficient there. And so that changes that to 2. So now that we have 2 sodiums on each side and 2 chlorines on each side, this is balanced, and we can move on with our question. All right, find the yield of sodium chloride in grams if 2.4567 grams of sodium is reacted with an excess of chlorine gas. So the variable that we're given is that we have 2.456 grams of sodium. And the thing that we're looking for is we want to find the yield of sodium chloride in grams. So we want to find the grams of sodium chloride. So just like last time, I want us to start off with the variable that we were given. And so we're going to say we have 2.4567 grams of sodium. All right. And like I said, for stoichiometry, you normally follow a set path of you want to convert to moles, because that's the only way we can go from one compound to a different compound. And looking at our question, we don't actually have anything at our disposal that lets us go from grams to moles. So what you need to keep in mind is whenever you're doing stoichiometry is you can pull out a periodic table. And using the periodic table, we can convert it to moles using the molar mass. So if we find sodium, we have this 22.99, and what that 22.99 means is that we have 22.99 grams of sodium is equal to 1 mole of sodium. And we can rewrite that as a fraction. I'm going to say we have 22.99 grams of sodium for every mole of sodium. Or we can write the reciprocal of that, since that's just equal to 1. I'm going to say 1 mole of sodium over 22.99 grams of sodium. So looking at our little railroad cross method that we've already set up, we need to have grams of sodium down here in the bottom. And so I'm going to use that 22.99 grams of sodium, and that's equal to every 1 mole of sodium. All right, so looking at cross-common units, we have grams of sodium over grams of sodium. So we're left in moles of sodium. Once we get to moles, that allows us to use our chemical equation, and we can say for every 2 moles of sodium, we can make 2 moles of sodium chloride. And you just want to use whatever these coefficients are. There are ways we could potentially reduce it down and everything, but it's best to just keep it simple, and whatever this coefficient is what you're going to be using. So we're going to say for every 2 moles of sodium, we can produce 2 moles of sodium chloride, so we can get to our desired compound. So we're going to have 2 moles of sodium for every 2 moles of sodium chloride. All right, now that we are in moles of sodium chloride, our desired species, now we have to convert to the desired units of it. So we have the correct compound, but we need to get down to the right units. And so since it's asking for grams, we can look back at our periodic table again and see that we can have sodium right here, 22.99, that's grams per mole, plus that chlorine, that Cl, that 35.45. If we add those numbers together, we'll get 58.44. So we're going to say for every 1 mole of sodium chloride, and I highly encourage you to just always use 1 mole when you're doing molar mass. For every 1 mole of sodium chloride, we have 58.44 grams of sodium chloride. And so now, since we have our desired units, we can go back and double check just to make sure all our units cancel. Grams of sodium cancel out grams of sodium. Moles of sodium cancel out with moles of sodium. Moles of sodium chloride cancel out with moles of sodium chloride. And we're left with grams of sodium chloride, which is what we're looking for. Now we can multiply everything on top. So we'll do 2.456.7 multiplied by 2, multiplied by 58.44. And then we'll divide by everything on the bottom. So then we'll divide that by 22.99 and then divide it by 2. So if we do all that, that will equal 6.244 8692. 86942 grams of sodium chloride. We want to look at our significant figures here. If we do that, we see that we have 5 significant figures there, 4 significant figures there. Whenever you're doing the mole-to-mole conversion or using the chemical equation, that is an exact number. We have for every exact 2 moles of sodium chloride, we needed exactly 2 moles of sodium. So that one's not going to limit you with significant figures. And then we have 4 significant figures there. So since we have 5, 4, and 4, the lowest one is 4. So we're going to be limited to 4 significant figures in this case. So we'll just count 1, 2, 3, 4. We're good down to the second 4. And so what this really is this is going to be 6.245 grams of sodium chloride. And we're just rounding it up because this 8 is greater than 5. All right. So this is the basic setup for how you do any type of stoichiometry problem. You always want to convert to moles. Oftentimes you'll be using molar masses to do that, so you'll be going from grams to moles that way. Then you want to use the chemical equation. Once you're in moles, you can use the chemical equation and figure out the mole-to-mole ratio. And then finally, you want to convert to your desired units. And oftentimes, not always, but oftentimes, that will be a molar mass as well. So you can always feel free to pull out your periodic table. If you're looking at a question and you don't know where to go from there, pull out the periodic table, and normally molar mass will help get you there. All right. So let's go ahead and we're going to try working on a little bit harder problem. This time, we're going to be combining both stoichiometry and unit conversions. So since we're kind of setting up this railroad across method, and now we know the trick with stoichiometry, you just need to use your periodic table and convert to moles and then use the equation, you'll see that all this is really just unit conversions. So this extra step hopefully won't be that big of a hurdle for anyone. All right, so looking at this problem, we have the process of producing metallic lead involves reacting lead 2 oxide, PbO, with carbon monoxide, CO, at about 1200 degrees Celsius. Then we have an equation, and we have PbO plus CO yielding Pb and CO2. All right, so we want to go through and go ahead and balance this. So I'm going to draw a line where my yield is, and we're going to look at the elements one by one for both the products and reactants. So if we look at lead, Pb, we can see that we have one lead over here, and that's the only one, so we're going to have one lead in our reactant side. And then we look at lead on the other side, we only have Pb right there, so we only have one lead in our product side. Then we can look at oxygen. All right, so for oxygen, we have one oxygen there and one oxygen there. So we add those together to get two oxygens on our reactant side. And then on our product side, this is the only spot with oxygens, and we have a little 2 subscript there, so we know we have 2 oxygens for the CO2. So we'll have 2 oxygens, so that's still balanced. And we have one more. Unfortunately, I'm a little bit out of space, so we'll just do carbons over here. I'll draw another line. All right, so looking at carbons, we have one carbon here and one carbon here. So one carbon for reactants and one carbon for the products. And so that's balanced as well. So this reaction is already balanced, and you could leave it as blank because they're assumed to be one, or if you want, you can go ahead and just fill in the ones. It's your choice. All right, so let's continue on with our question. 1 mole of carbon monoxide occupies 5.27902 cubic feet at 1 atmosphere of pressure at 1200 degrees Celsius. What would be the minimum volume in cubic feet of the carbon monoxide filled oven to convert 5.000 grams of lead oxide to pure metallic lead? Now, this question is a little wordy and has some extra numbers in there. So we have to go through and figure out what it is that we are starting out with and what we're actually looking for. All right, so we want to try to find the variable. And the variable in this case is going to be the 5.000 grams of lead oxide. And what we're trying to look for, it says what would be the minimum volume in cubic feet of the CO filled oven. So we're looking for essentially cubic feet so that we can hold enough carbon monoxide in there. So cubic feet of carbon monoxide. All right, so now we know our starting point, we know our ending point, and since we're going from one compound to another compound, we know we're going to have to kind of a mid-stopping point at the chemical equation. So let's go ahead and start off with the 5.000 grams of lead oxide. So we have 5.000 grams of lead oxide. All right. Now we want to work on getting this to moles. That's going to be our first goal, just like last time. And so when we do that, we're going to be using that chemical, we're going to be using the periodic table again. And I'm going to pull that back up so we can look at it. So we're looking for lead, and we see it's right down here, and it's 207.2. So 207.2 grams per mole, and we need to add that with oxygen. So we're going to add 16 to that. All right, so when we do that, we're going to get 223.2 grams of lead oxide for every 1 mole of lead oxide. All right. Now that we're in moles of lead oxide, we can use our chemical equation. I know I want to put moles of lead oxide on the bottom. And looking at our chemical equation, we have lead oxide here, and we're trying to convert it to, and we need to figure out something, but ultimately we're trying to figure out how much CO we need. So we're going from lead oxide to CO. So whenever you're using your chemical equation, you can use it to convert from reactants to seeing how much of another reactant you need, which is what we're doing here. Or last time when we're going from a reactant to a product. You can use it to convert to any species along this chemical equation. It's just a matter of what you're actually looking for. So in this case, we're going to go from 1 mole of lead oxide to 1 mole of carbon monoxide. So we'll say 1 mole of lead oxide for every 1 mole of CO. All right, now we need to try to get to cubic feet. So we need to look and see if there's any kind of conversions that we have that have moles of carbon monoxide or moles of CO. And if we read the question, we can see that we have 1 mole of CO occupies 5.29 or 5.27902 cubic feet. So we have a bunch of extra numbers in here, but the one that's actually important is this one, and it's for every 1 mole. So we're going to say for every 1 mole of CO, we have 5.27902 cubic feet of carbon monoxide. All right. So now we got to our desired unit. We want to double check, make sure all the other units have canceled out. So we'll see grams of lead oxide on top, cancel out the grams of lead oxide on bottom, moles of lead oxide on top, moles of lead oxide on bottom, moles of CO on top, moles of CO on bottom, and that leaves us with cubic feet of CO not canceling out with anything. So that's our desired units, and we still have them. So that's where we're going to stop. So now we can multiply everything on top. We're going to multiply the 5 by the 5.27902, and then divide by everything on bottom, the 223.2. When we do all that math, we get 0.118258 cubic feet of CO. And then we can go back and look at our significant figures. You can see that we have 4 significant figures there, 4 significant figures there, and then we have 6 significant figures there. So we have 4, 4, and 6. We're going to be limited to 4 significant figures, so we're going to be limited to that 2. The 0 over here is just a placeholder, so it's not going to count towards our significant figures. All right, so we can go ahead and rewrite that. We get 0.1183 cubic feet of carbon monoxide. So our oven would have to be 0.1183 cubic feet in order to hold enough CO to convert 5 grams of lead oxide into pure metallic lead. All right, great. So that was a fairly simple conversion. The problem was a little wordy, but let's go ahead and we'll try to look at one that's even a little bit more difficult. So for this one, we're going to have a bunch of conversions, and we just have to keep trucking along. As long as we keep track of our units, this shouldn't be too bad. So the question reads, combustible hydrogen and oxygen gas can be retrieved from simple water, H2O, by applying a current through the liquid. This is electrolysis. And we're given an equation where we have H2O yields H2, hydrogen gas, and O2, oxygen gas. So since we have a chemical equation, let's go ahead and balance this. We can go ahead and draw a little line right here, and we'll look at our amount of hydrogens. So on the reactant side, we have a 2 there, a little subscript. So that means we have 2 hydrogens on the reactant side. We look on the product side, we have a little 2 subscript there, so we have 2 hydrogens in the products. Now we can go ahead and look at oxygens as well. When we look at oxygens, we'll see that we don't have any subscript there, so this is just a single oxygen. And then when we look on the product side, we see we have a 2 subscript, so we're going to have 2 oxygens over there. So to make those equal, we are going to put a 2 coefficient in front of the water, the H2O. And so that's going to change our oxygens to have 2 of them, but it's also going to change our hydrogens to have 4 on the reactant side. So in order to make that balanced, I'm going to go ahead and add a 2 to the H2 on the product side to bump that up to 4. All right, so now that our equation is balanced, we'll go ahead and read the rest of the question. If 52.3456 milliliters of water undergoes electrolysis, how many milliliters of oxygen gas is produced? And then we're given some additional information. At STP, oxygen has a density of 1.429 grams per liter. Also, 1 milliliter of H2O is exactly 1 gram of H2O. So we need to decide what is our variable that we're starting out with. In this case, it's going to be our milliliters of water. And then we need to figure out what we're looking for. Where are we trying to get to? And this is going to be how many milliliters of oxygen gas, are produced. So let's go ahead and start off with our variable. I'm going to write that down there. We have 52.3456 milliliters of water. All right, so now I need to convert this to something, and I know I want to have milliliters of water on the bottom. So I can go through and look through my question, and we can see that 1 milliliter of water is exactly 1 gram of water. So it's written in words, but we have 1 milliliter is equal to 1 gram for water. So we'll say 1 milliliter of water is equal to 1 gram of water. All right. So now I need to convert this to something else. We're ultimately trying to get to moles, so we can convert to oxygen. And we need grams of water. And we do have something with grams in it. We have this 1.429 grams, but this is for oxygen. That's not actually water. So what we need to do is we need to go back to our tried and true thing when we can't find anything else. Well, we want to make sure that we can go ahead and use our periodic table. And so we'll go back and look at our periodic table, and we can look at hydrogen. It's 1.008. Since we have 2 hydrogens, we're going to multiply this by 2, and then we're going to add that to oxygen of 16.00. All right, when we do that, we should get 18.016 grams of water for every 1 mole of water, or mole of H2O. All right, now that we're in moles of water, we can look at our chemical equation, and we see that we have 2 moles of water for every 1 mole of O2. So I'm going to just write that down here. We're going to have 2 moles of H2O for every 1 mole of O2. All right, so now we got to our desired compound of O2, and we want to try to figure out some way to get to milliliters. Now, one of the conversions given to us was this density here, this 1.429 grams of O2 for every liter of O2. Well, we can't go from moles to milliliters directly, but what we can do is we can go from moles to grams using our molar mass. So if we look at oxygen, we can multiply that 16.00 by 2, and we'll say for every 1 mole of O2, we have 32.00 grams of O2. All right, so we're just using the molar mass there, convert it to grams. Now we can go ahead and use this equality that was given in the question. And so we can put in 1.429 grams of O2 for every liter of O2. All right, and the question is asking for milliliters. And we can convert from liters to milliliters by saying that for every 1 liter of O2, we have 1,000 milliliters of O2. All right, so now we can go back and double check all of our units canceling out that we would need to cancel out. So we have milliliters of O2 cancel out with milliliters of O2, grams of H2O cancel out with grams of H2O, moles of H2O cancel out with moles of H2O, moles of O2 cancel out with moles of O2, grams of O2 cancel out with grams of O2, liters of O2 cancel out with liters of O2, and then we're left with milliliters of O2. So we got to our desired units. Now we need to multiply everything on top, so 52.3456 multiplied by 32, multiplied by 1,000, and then divide that by all the numbers on the bottom, so divide by 18.016, divide by 2, and then divide by 1.429. So if we plug all that in our calculator, then we can calculate that out, and we'll get 32,531.91 milliliters of O2. Then we can check our significant figures. And for his first number, we have 6 significant figures. For the second one, we're actually only good to that 1 because of the oxygen limiting us to the hundredths place. So we have 4 significant figures there. We have 4 significant figures there. We have 4 significant figures there. And then the last one is an exact equality. So we're going to be limited to 4 significant figures overall. So we're good down to that second 3. So when we write out the final answer, this would be 32,530 milliliters of O2. All right, so that one had a lot of conversions in it. But again, if you just keep track of your units and keep trying to cancel out all the units, you'll eventually get there. All right, so now let's go ahead and move on to one with a little bit more difficult conversions in it. All right. So NOS is used in performance vehicles and aircraft to boost output and speed. Part of the reason for this increase in performance is the change in volume, for which an increase in moles of gas is a major contributing factor. In the reaction, nitrous oxide, N2O, or NOS, is heated to create nitrogen, N2, and oxygen, O2, gas. Then we're given an equation. And so we want to go ahead and solve for that. So we're going to just take a look at both of our reactants and products. Go ahead. So we're going to just take a look at our reactants and products. We'll look at nitrogen first. So on the product side, we have 2 subscript there, so we have 2 nitrogens. And then on the product side, we have a subscript 2 there. So we're going to have 2 nitrogens on there as well. Then we look at our oxygens. And this is where we're going to not have a real big issue, but we're going to have a little issue. Right here we have 1 oxygen on the reactant side, and then on the product side we have 2. So in order to make those equal, we're going to put 2 coefficient in front of the N2O. So that's going to change oxygens to being 2, so those are even. But now that also changes our nitrogens to being 4 on the reactant side. And so to get 4 on the product side, we're going to put a coefficient of 2 in front of the N2. All right. So with that, each element is the same on both the reactant side and product side, so it's balanced. And we'll continue reading on with the question. You heat 1.3567 milliliters of N2O to 577 degrees Celsius within your single cylinder vehicle. How many milliliters of each product, both N2 and O2, is formed within the cylinder? And then we're given some extra information here with some densities at that temperature and pressure for N2O, N2, and O2. All right, so like I said, this one's a little bit harder. It has some more conversions in it, but same thing holds true. We just need to find what the variable was that was given to us and figure out what we're trying to finally get to. So looking at this, we can see that our variable is this 1.3567 milliliters of N2O. So that's where we're going to start. And we're trying to get to how many milliliters of both N2 and O2. So in this case, I want us to go ahead and essentially break it up, and we're going to treat this like 2 separate problems because it ultimately is 2 separate problems. So when we split this up, we're going to start and we'll try to find the amount of N2 first. So we're going to have 1.3567 milliliters of N2O. And we need to figure out some sort of conversion that has milliliters of N2O in it. But I'm not seeing any that have milliliters. One thing that I do see is that we have this grams and liters down here. So we can convert to liters, and maybe that'll get us somewhere. So I'm going to say that we have 1,000 milliliters of N2O for every 1 liter of N2O. All right, now that we're in liters of N2O, we're going to want liters of N2O down here. And that same area I was looking at earlier, that density here, we can go ahead and use that value here. So for every 1 liter of N2O, we have 0.63499 grams of N2O. All right, so now that we're in grams, we want to convert from one compound to another compound, and we want to get to moles. So one of the easiest ways to get to moles after you get to grams is to use the periodic table. So we can just use the periodic table here, and we can look at our nitrogen. We're at 14.01. We can multiply that by 2, and then we can add that to the oxygen of 16.00. And so when we do that, we should get 44.02 grams of N2O for every 1 mole of N2O. Then, now that we're in moles, we can go ahead and look at our chemical equation here. So we have 2 moles of N2O for every 2 moles of N2. And so we'll just put that there. I'm going to go ahead and remove my periodic table. All right, so we're going to put 2 moles of N2O for every 2 moles of N2. Now that we're in moles of N2, we could use the periodic table again and do 14.01 times 2 to get our moles, our molar mass of N2. So we'll say for every 1 mole of N2, we're going to have 28.02 grams of N2. Now that I'm in grams of N2, this is going to allow us to go ahead and use this density here, where we can go from grams to liters. All right, so, and again, whenever you're using these numbers here, keep in mind that whatever this number is goes with this unit that's above the line or the slash. All right, so we're going to have 0.40182 grams of N2 for every liter of N2. And then we ultimately want to get to milliliters of N2. So we just have one more conversion to go. We can say for every 1 liter of N2. Again, you can use your useful equations packet or just know that this conversion where you have 1,000 milliliters is equal to 1 liter. All right. So now we can go back and confirm that all of our units cancel out except for the ones that we want. So milliliters of N2O on top, milliliters of N2O on bottom, those cancel out. Liters of N2O on top, liters of N2O on bottom, those cancel out. Grams of N2O on top, grams of N2O on bottom, those cancel out. Moles of N2 on top, moles of N2O on bottom. Then we have moles of N2, grams of N2, grams of N2, liters of N2, liters of N2, and we're left with milliliters of N2. So now we can multiply everything on top. We'll multiply the 1.3567 by the 0.63499, multiplied by 2, multiplied by 28.02, multiplied by 1,000, then we'll divide by 1,000, divide by 44.02, divide by 2, and divide by 0.40182. All right, when you do all that math, you're going to get that to be equal to 1.36470020 milliliters of N2. We can go back and look at significant figures. All right, there we have 5 significant figures. There we have 5 significant figures, 4 significant figures, 4 significant figures, and 5 significant figures. So we're going to be limited to 4 significant figures. So we're going to be good down to that 4. And since we have another half the problem, I'm going to just write this out over here. And it's going to be 1.365 milliliters of N2. So that's one of our solutions. Now we need to find the other one for oxygen. So for oxygen, we're going to set this up in a very similar fashion. Now I'm going to go through this just a little bit faster. All right, so we're going to have basically the same starting thing that we had last time. So we're going to have that 1.3567 milliliters of N2O. And basically it's going to be the same all the way up until we get to the chemical equation. And that's this part where it's going to differ a little bit. So we're going to have 1,000 milliliters of N2O for every 1 liter of N2O. And then for every liter of N2O, we're going to have 0.63499 grams of N2O. Then we'd be able to use our periodic table, and we say for every 44.02 grams of N2O. We have 1 mole of N2O. Now this is going to be where it changes. All right. So we did our moles and moles. Now we're going to look at our chemical equation, and we'll see that for every 2 moles of N2O, we only have 1 mole of O2. So we're going to say 2 moles of N2O. It's going to give us 1 mole of O2. Then we can use the periodic table, and we'll say for every 1 mole of O2, and just plug in that molar mass, so 16 times 2, so we get 32.00 grams of O2. And then we can look at our question, and we can see that we have this density of O2, so we can go from grams to liters. So we're going to have 0.45914 grams of O2 for every 1 liter of O2. And then we can do our final conversion of 1 liter of O2 is equal to 1,000 milliliters of O2. All right, then we can multiply everything on top. We'll multiply 1.34357 by 0.63499 by 32 by 1,000. Then we can divide by 1,000, divide by 44.02, divide by 2, and divide by 0.45914. And if you do all that, you get 0.6819861 milliliters of O2. And we can go back and look at our significant figures. And we can say that we have 5 significant figures there. We have 5 significant figures there, 4 significant figures there, 4 significant figures there, then 5 significant figures there. So we're going to be limited to 4 significant figures again. So we're good to that 9. All right, so now we're going to have to round it, and we're going to get 0.682, and we need to go ahead and include that 0, even though that 9 rounded up, to show our level of precision. Milliliters of O2. So this is our second response. All right. So that problem was a little bit more difficult, had more conversions, maybe a little bit tougher conversions. But it's still fairly achievable as long as you keep track of your units. So now we're going to try a much harder problem. And this one is going to involve throwing in some other concepts you may have learned in chemistry thus far. So let's go ahead and clear that out. All right. So in this particular one, we're going to be utilizing molarity and limiting reagents. So let's go ahead and read that problem. All right, so we have you're demonstrating the use of common antacid tablets as an experiment in your laboratory. To simulate stomach acid, you prepare a solution of 0.1604 molar HCl. Now, molar is the capital M, and basically what that means is you're going to have moles of whatever analyte you have per liter of solution. So in this case, with that 0.1604 molar HCl, what that is really saying is that we have 0.1604 moles of HCl for every liter of that solution. All right, so for every liter of that solution, oftentimes how I will write that will be whatever that concentration is, so 0.1604 molar HCl. All right. So we're going to be using molarity. And then the other thing we're going to be using is limiting reagents. So where that comes into play is when we decide where we want to start, which we'll talk about in just a second. So you use 0.31 gram tablet of antacid where calcium carbonate is the only ingredient, and mix it with 25.00 milliliters of 0.1604 molar hydrochloric acid. Then we're given an equation where we have HCl plus calcium carbonate, or CaCO3, yields water, or H2O, plus calcium chloride, CaCl2, and carbon dioxide, CO2. And let's go ahead and balance that out. All right, I'm going to just do the reactants and products over here so I have a little bit more space. So we have our reactants and products. All right, so a couple different ways you can approach that. I'm going to just go down the line with all of this. So we look at our hydrogens. On the reactant side, we have 1. On the product side, we have 2. So we have 1 right there, and we have the 2 right there. So in order to make those equal, I'm going to go ahead and multiply the HCl by 2. And so now we'll have 2 hydrogens on each side. And then we're going to look at chlorines. So for chlorine, we need to take into account this coefficient right here. We have a 2 already. So we have nothing right here. So we have 1 chlorine in this molecule, but we have 2 of those molecules. So we're going to have 2 chlorines on our reactant side. Then I look at our product side. We have a subscript 2 right there. So we're going to have 2 chlorines. So those are good. Now we're going to look at our calcium, Ca. All right, on the reactant side, we just have the single Ca. And then on the product side, we have a single Ca as well. All right, now we can go ahead and look at carbon. All right, for carbon, we have 1 over here. And we also have just 1 over here. So 1 for each of those. And then we can look at oxygens. All right, so for oxygens, we have 3 on our reactant side. And on the product side, we have 1 from H2O and 2 from CO2. So we're going to have 3 oxygens on our product side. So all those are balanced. Each element is the same for the reactants compared to the products. So it's balanced. So now we can move on with the rest of our question. How many grams of the salt, calcium chloride, or CaCl2, are created? All right. So first thing we want to do is figure out where we can begin. So we have 0.31 grams of our antacid tablet, which is calcium carbonate. It's the only ingredient. So we have calcium carbonate, or that's CaCO3. But there's another spot we could have can start. And it says, and we mix it with 25 milliliters of our solution, of our HCl solution. So whenever you're given essentially both reactants, that is a telltale sign that this is going to be a limiting reagent problem. And the easiest way to solve that is to treat it like 2 separate problems, and then we'll evaluate it at the end. It's pretty much whichever one you get the least amount of product with is the actual answer, because you ran out of that reactant. All right, so we're going to do 2 problems here, and we want to figure out where we're trying to get to with both of those. So we need to figure out how many grams of calcium chloride we're making. So to do this, we're going to go ahead and we'll start off with the grams of calcium carbonate first. So let's go ahead and write that down in here. So we have 0.31 grams of calcium carbonate. Then we need to cancel that out with grams of calcium carbonate. So we can actually go through and look at our periodic table. When we look at our periodic table, we're going to be looking at the calcium right here, this 40.08. We're going to add that to carbon, 12.01, and then add that to our oxygen. And we have 3 of those, so we're going to do 16.00 multiplied by 3 and add all those together. When we do that, we get 100.09 grams of calcium carbonate. And then we're going to have that for every mole of calcium carbonate. And now that we're in moles of calcium carbonate, we can look at our chemical reaction. And we see that for every 1 mole of calcium carbonate, we make 1 mole of calcium chloride. So it's just a 1-to-1 ratio. So we're going to write 1 mole of calcium carbonate is equal to 1 mole of calcium chloride. And since we're looking for grams of calcium chloride, we're going to go through and we'll have to use the molar mass again. So we're going to say for every 1 mole of calcium chloride, then we can go through and look at our calcium of 40.08 grams, and then our 2 chlorides, each being 35.45. So we'll multiply that by 2 and add that all up together, and we get 110.99 grams of calcium chloride. All right, then we want to double check our units. Make sure that everything cancels out that we need to cancel out. We'll have grams of calcium chloride cancel out with grams of calcium chloride, moles of calcium, grams of calcium carbonate cancel out with grams of calcium carbonate, moles of calcium carbonate cancel out with moles of calcium carbonate, moles of calcium chloride cancel out with moles of calcium chloride, and then we're left with grams of calcium chloride. So when we get that, that's going to be equal to 0.344 grams of calcium chloride. And we can look at our significant figures. We're going to be limited to 2 sig figs there. This one's going to have 5. And then we're going to also have 5 over here. So we're going to be limited to 2 sig figs. All right. So that's kind of half of the problem. If we knew calcium carbonate was our limiting reactant, we say, all right, we're good, we're done, but we don't know. So we need to go ahead and figure it out for the HCl as well. We need to figure it out for the other reactant and how much that can make. And so we're going to go ahead and start off with our 25.00 milliliters of HCl solution. 25.00 milliliters of our HCl solution. So this is the 0.1604 molar HCl. And in order to get to that molarity, which we kind of drew out here, we need to get to liters. So right now we're in milliliters of solution, so we need to just convert it to liters. So we're going to say for every 1,000 milliliters of our solution of 0.1604 molar HCl, we're going to have 1 liter of 0.1604 molar HCl. Now you can label this however you want. Some people like to label it as solution 1 or solution A. I like to put the concentrations down so if I go back and look at it, I know what it was. But use whatever you want. Now we can use that molarity that we wrote up earlier, so we can convert from liters to moles of that solution. So we're going to say for every 1 liter of this solution of 0.1604 molar HCl, we have 0.1604 moles of HCl. All right, so whenever using molarity, one thing to kind of watch out for is we didn't have to use the periodic table to find the molar mass, and you don't have to. We're just trying to get to moles. And the nice thing about molarity is you don't need the periodic table and molar masses to get to moles. We just need the initial volume, and then we can convert it with the actual molarity here to get to moles. So at that point, we are essentially done with that first step for stoichiometry, and we've converted to moles. So we can just look at our 2 moles of HCl is equal to 1 mole of calcium chloride. All right, so you don't have to do molar mass for that section. All right, so let's go ahead and continue on here. All right, so we got for every 2 moles of HCl, we have 1 mole of calcium chloride. And you'll see this is pretty much the exact same that we had earlier. I'm going to get rid of my periodic table so I have a little bit more space. All right, and then for every 1 mole of calcium chloride, we can use the molar mass, which are converted, which was 110.99 grams of calcium chloride. So with that, we can go back and double check our units to make sure everything cancels out that needs to cancel out. We'll have milliliters of our solution, cancel out with milliliters of our solution, liters of our solution, cancel out with liters of our solution, moles of HCl, cancel out with moles of HCl, moles of calcium chloride, cancel out with moles of calcium chloride, and then we're left with grams of calcium chloride, which is what we're looking for. And when we do that one, we can multiply everything on top, so 25 times 0.1604 multiplied by 110.99, and then divide by everything on bottom, so dividing by 1,000 and dividing by 2. When we do that, we get 0.222535 grams of calcium chloride. We can go back and look at our significant figures. There we have 4 significant figures, and there we have 4 significant figures, and there we have 5 significant figures. So we're going to be limited to 4 significant figures, so we're good to that 5. All right, so now we're at the limiting reagent part, and we need to compare the 2 numbers. So coming from the HCl, we have 0.2225 grams of calcium chloride. And we're going to be comparing that with the 0.34 grams of calcium chloride if we had solved it for the calcium carbonate to begin with. And we need to find which one is the lesser value. So 0.2225 is less than 0.34. And so our final answer would be the 0.2225 grams of calcium chloride. All right. So this is probably one of the harder types of stoichiometry problems you would have, where we're involving multiple other things. But again, as long as you keep track of your units, you should be okay. And you can still apply other topics that you've learned already, such as limiting reagents and molarity to stoichiometry. But the big thing is just keep track of your units, and you should be fine. So hopefully you found that useful, and I look forward to seeing you in the next video.